Hello and welcome to my Tech Fun. My name is Igor, and in this video I would like to talk about 3D printing closed loop timing belts. I know I already can see comments why to print something like that when you can buy. Yes, definitely, then you are looking wrong channel. I mean, I got so many comments when I did the videos about 3D printed bolts and screw nuts. And for example, for open loop, I already have, I don't know, 10 meters of spare timing belt, and I cut it on the proper length. But closed loop I don't have any size, and when I did a review of Ming the Magician X, usually I print something from TPU when I do direct drive extruder review, and usually I print something like this is the corner guard for our desk, but I don't need so many corner guards, so I decided to print something else, and I downloaded a timing belt from Thingiverse and I printed it. From that I know that my question is not if we can use 3D printed timing belts, but what are those applications where we can use these printed timing belts. Now for this, of course, we need some testing, and I'm sure that I will have already two applications where I will use this type of the timing belt. One is I'm doing some DIY turntable, and the other is something from the busy board for our youngest daughter. In this video I talk about design, and then about the print settings which work for me, and then about different materials for this application, and then the mechanical testing, which will include the tensile test, so what is the maximal load before it breaks, the elongation of on a given load, torque test, and some kind of durability test. Okay, before I start, so I will test most common timing belt which I use in 3D printing hobby, and that's the 2GT or GT2. As you can see, I already started with the printing test objects, but for testing the design and the different materials. So let's start with the first point, and that's the design. So this is the first one which I downloaded from Thingiverse and I printed, and it's not visible here, so but it has three lines, three walls. One is the teeth, and then two lines of the additional wall, and it is usable maybe with some bigger diameters, but it is a little bit rigid. As you can see, it lies very nicely on this pulley, but I have to apply a little bit bigger force until it's completely on this pulley. It is not a problem with if you are using some kind of bigger pulley with a bigger number of the teeth, but that's why I decided to create my own design, and I reduced the number of the walls. So number 2, it has only two walls. One is the teeth and the other is the outer wall. An extremely small force I need until it's completely around the pulley. Now the problem with this design is that I followed exactly the geometry of the GT2 belt. And now, well, under the microscope it is more visible, I have a small hole below the teeth, which will make them weaker. So I create a new design, and I reduce this outer diameter, so now the height of the teeth is the same, but it's a little bit narrow, so I reduce the gap, the hole below the teeth. And if I increase the line width or the flow rate, I can get even better results. 4, 5 and 6 are actually printed with only one wall. So we have the teeth on one side, but as I mentioned, it's only one wall. This means we can see from the outer side also that it goes in. And I feel it's a little bit elastic, and it doesn't keep the geometry so good. If I put some tension on it, I can feel that it stretches a little bit, and that is not good with our timing belts. So that's why I dropped this idea, and so the best design I could figure out is actually with number 3, and that's using two walls, actually teeth and one wall, and reduce more narrow teeth. So in this case we have smaller gap below the tooth. Now let's talk about print settings. Now first I tried with random seams, you know, when it starts the next layer, and with this the closing of the loop is always on a different position. In that case I thought it is stronger Maybe it is, I didn't test it yet, but with this I have a lot of stringing, which is not so hard to remove. It depends on the material you are using, but definitely if the seams are always on the same spot, in that case, well, in theory maybe it's weaker on that spot, I will test it later, but in that case I got much nicer printings without these stringings. So if you want to compare these two, as you can see, these are random seams and I have a lot of stringing, and this is printed with the seams only on one line, and I cannot actually even see the seams. Maybe they are from inside, but basically I didn't have to clean this at all. Additional advice: Z-hop 0, but if you don't have the random seams, that's not even important. Fill gaps no, or no gaps in different slicer, to avoid filling these holes behind the teeth. As already mentioned, if I increase the line width or the flow rate, the quality may be even better because these holes will be filled and the walls may be stronger. Retraction always 0 or very minimal with the TPU, and my settings usually are 240 degrees for the nozzle and 50 degrees Celsius on the bed, and approximately I'm using 50% of the cooling. Now let's talk about the material. Obviously it has to be flexible. Just to show you, this is from PLA, and as you can see they are engaged, the teeth, but I cannot apply normally very big force to get those timing belt completely around the pulley. Oh, it's even broken now on the seams. Okay, so definitely we need some kind of TPU or flexible filament. Actually, the real timing belt is usually made from some polyurethane, but it is also reinforced, and that reinforcing is not there to not to break, but to reduce the elasticity as much as possible. Because if it is elastic, that's the problem, because it's okay, it goes around the pulley very nice, but imagine on printer you are using it on x-axis and it has to stop because you want to start moving in y-axis, but if it doesn't stop immediately because of that elasticity, it will vibrate a little bit, but it's already moving in y-axis, so that's why we got those ghostings on the printing. So even these are not really perfect, but of course they are much better. That's why I mentioned that yes, they are usable, but depend of the application type. Okay, so we need some kind of TPU. Now the TPU can have different hardness. This is the hardest which I have at home, and that's the 98 on Shore A scale. This is on 95 and this is 92. And in the meantime I printed this one. This is Shore 85, but definitely this is too elastic, but actually it looks great. Now for the filling, I think the best is between two, so or 98 or 95. I will measure later the elasticity, so that's where I will decide which is better on mechanical testing actually. Now before I move to the mechanical testing, it is important to clear one important fact, and that's the pulling force. Now as you can see, the tooth of the timing belt goes into the pulley without any problem, but if I don't apply enough pulling force, in that case they may skip. So this means I have to apply some pulling force, and in that case the teeth stays engaged and we can apply transmit bigger torque. But unfortunately this maximal pulling force is limited by the bearings inside the stepper motor. The pulley goes on the shaft of the stepper motor, and this is a little bit smaller one, but I tried to search on different sources, and in most cases I found that the maximal radial force is approximately 28 or maximum 30 newtons, and if you divide with the G, that's approximately 2.9 kilograms. And this will be my base for torque test or durability or for elongation. I want to see how it will perform, I mean these printed timing belts, on approximately 2.5 kilogram load, because this weight I have at home, and this will be my tension on this pulley and timing belt. And it's time for mechanical testing. I have here a 1-ton chain hoist and half-ton crane scale, and this is my test setup, and I will pull it until it doesn't break. Now I will not test on a real timing belt here, only those 3D printers, but this is my favorite experiment, so I will do with a lot of different variations. And I will record this with two cameras. One will record only the test object, but the second camera will be on the crane scale to see the braking load. And because I want to show you, or maybe even to measure somehow, the elongation. I will separately test with the calipers the elongation for the given load, but now the primary is the testing the braking load. I'm starting with one valve version with the hardest TPU I have in this experiment, with the 98 Shore A. Then 3 valves version. I will show you the results later. The next one is 2 valves, but with random seams. This should be stronger theoretically. And then the same 2 valves, but with the line seams.
And it broke exactly on the seams line.
And then this is the softest TPU in this experiment. And it also broke on the seams, but with very long elongation. And this is the 94 Shore A scale.
And it also broke on the seams line, but now it is in quite good shape. I cannot see permanent deformation on it.
And this is how they look like after the breaking. In this experiment I want to measure the deformation under the load, and in this test I will include the regular timing belt too. First I place this half-kilogram load because I need it to be stretched, and then I can measure the distance. Then I will place a 2.5 kilogram load on them. I will measure the length, the distance again, and I will leave this for at least 1 hour, and after 1 hour I will measure the length again, and I will go back to half kilogram and then measure that length too. The reason for this delayed measuring too is that I want to see is there any creeping, the deformation under the constant load, because it is not good for timing belts. If we place some tension and lock the position of the pulleys, we want the tension to stay. But if it lost the elasticity because of this creeping, the tension will be smaller and the maximal transmitted torque will be reduced. I'm starting with regular GT2, this is half kilograms. $89.56. And now moving to 2.5 kilogram load. $89.87. Now let's measure the softest timing belt in this test. $91.97. Moving to 2.5 kilograms. $102.75. Now the hardest in this test. $89.62. $91.98. And the last one here. $89.66. $93.03. One hour pass, and I will repeat the same measuring now, but in reverse order. 95.04. 91.59. This video is too long anyway, so I will speed up this part and I will show you the results at the end in the summary. I measured everything and I wrote down to this table, but I will show you the results at the end. But unfortunately, bad news for us 3D printer owners, because with this I don't have almost any deformation, but with this there are some quite a lot permanent deformation too. This is my test setup for torque test, and as you can see I have two shafts. This one is fixed, but this one can rotate. I even have a ball bearing here. Now the maximal torque depends on the several things. One is the geometry of the teeth, but it is quite good with the 3D printing versions I check under the microscope. But the second is the tension on the timing belt. And that will be controlled. I will place here 2.5 kg load and then I will tighten these bolts. So the start tension will be the same. But very important question is what will happen after 1 hour. If there is some creeping, in that case it will lose that tension, and after 1 hour the maximal torque will be significantly reduced. I tied these bolts and now theoretically I have a 2.5 kg tension on this timing belt. Let's measure the torque. And now let's see when will this skip. Zero 0.6. 0.6. And let's see what is the situation after 1 hour. Still 0.6. So this regular timing belt holds the position quite good, of course, because it is reinforced. But now let's see our 3D printed versions. This is the hardest version of 3D printed timing belt, Shore 98. Probably the initial torque will be similar, but let's measure it. No, it is below 0.3 Newton meters because that's the lowest limit of this torque meter. But I still want to measure it somehow, so I'll try to use this open-end wrench and this small hanging scale, and I will calculate it because I know the length of this arm is 10 centimeters. .1 kilograms approximately on 10 centimeters. 0.1 kilogram, that's approximately 1 Newton. And if I multiply with 0.1 meter arm, that's 0.1 Newton meters. I don't think there is a need to test it after 1 hour after this. This is a time-lapse video of replacing from hardest to softest TPU in this experiment. This was approximately 4 minutes of assembling. So this is the softest TPU in this test, and let's put the load on it. Interesting to see very big stretching. And now the measuring that probably it is not measurable with this torque wrench. No, 0. So it is below 0.3 Newton meters. .085. Let's see how will it pull it back when I lose these bolts. And again approximately 4 minutes of assembling, moving from the softest to middle 94A TPU. And again placing the load. Quick test with the torque meter, but probably it is not measurable. No, so below 0.3 Newton meters. I think 0.085 was the peak. I'm a little bit disappointed, so 0.6 versus, I don't know, 0.1 Newton meters, that's huge differences. So these timing belts are reinforced with the reason. Of course, it doesn't mean they are completely useless, but that application must transmit very, very small torque. And in this part I will have some kind of the durability test, nothing special. I have here the stepper motor, and it will rotate this shaft 4 rotations approximately in one direction, and then 4 rotations in the other direction. Not exactly 4, but near. And I will see if it will work correctly after even 1 hour, for example. I can see it's quite good tension, so I place here the 2.5 kilogram tension on the timing belt. And let's give the power to the Arduino and to the motor, and let's start the experiment. Now, after approximately half hour of running, it works still perfectly. From the arrow I can see that the timing belt didn't slip on the pulley. And for the feeling, it still have the same tension which I placed at the beginning. Well, for the feeling, probably it's a little bit weaker, but I cannot feel with my finger. And now after 1 hour it is still running perfectly, and I can see that from this arrow and from this marking on the timing belt. So this means that there was no slipping between the belt and the pulley. Now one more thing I want to check, and that what will happen if I stop the pulley. Theoretically, the torque of the stepper motor is 0.4 Newton meters, and you already saw that this timing belt can transmit maximal torque of 0.1. So probably we can hear that sound when the timing belt will jump over the pulley. As I predicted, so this is much stronger than the torque which can transmit this timing belt. I can feel that the tension is very similar to one which I placed at the beginning, so maybe there is some creeping, but I cannot feel it by my finger. So yes, this can be used, but as I mentioned, transmitting very small torque. So even after 1 hour of using, I cannot see any damaging or wearing of the timing belt. Let's analyze the results, starting with tensile pulling test. And here we can see the brake load in kilogram, and also very interesting maybe the brake length. So we can see the softest filament, it extends to 6 times to its original length before it broke. But I tried to follow the load after 10 mm deformation, and in most cases this is far above the maximal tension I want to use on these timing belts, which is 2.5 kilograms. Also very interesting data that it's clear that the random seams is a little bit stronger compared to the line seams, but we don't have to use the random seams because again this is far above that maximal tension we want to use on the timing belt, and with the line seams we don't have that stringing and we have much nicer printing. The next is the prolongation, actually the length on the given load. This is the length on 0.5 kilogram load, and this is under a 2.5 kilogram load, and these are after 1 hour. Now to compare this better, I took this as 100%, and I calculate the changes in percentage. So on real GT2 we don't have any changes almost at all. From these three you can see that basically the Shore 98, the hardest, is the closest to this perfect results. And then the maximal torque, well, here we can see huge difference, especially here in the graph. So with the real GT2 the skip torque was 0.6 Newton meters, and with these three approximately 0.1. Of course we can improve this, but you are using bigger diameter pulleys or similar, but in this comparison, as you can see, huge difference. And now the conclusions. Well, at the beginning of the video I was much more optimistic, but after that torque test that was very disappointing. Maybe those negative commenters will be right, why to 3D print these timing belts when you can buy them. But I think that actually there are applications where we can use these printed versions, in those applications where we don't have big torque, just to move something. I know I have one, for example, I mentioned earlier that turntable when I want to reduce high RPM for the small DC motor to the rotation of the table. And actually there are methods where how can we improve this torque. I didn't measure it, but I know that if we use bigger diameter pulleys, in that case more tooths are engaged, and in that case the transmitted torque will be bigger. Of course we can use also different geometry, but I tested with this GT2, this have some kind of rounded tooth, so maybe it's easier for the belt to slip over the pulley. So probably different geometry, different type of the belt is better for this, but I tested this one as I mentioned earlier. About the materials, well, hardest is the better. Basically not the hardest is important to us, but to avoid the elasticity. So on short scale 98 or 95 or something between is probably the best in this case. About the design, well, for me this 2-valve version worked the best, but don't forget to disable the filling the gaps, and forget about retraction. You can use the seams in one line. Yes, it's weaker on that point, but that's far over the tension you will use on this pulley. So definitely in that case you don't have that stringing, you have much nicer printed timing belt. In one of my next videos I will show you step by step in Fusion 360 how can you design these timing belts. This one version you can download the STL from my website. I don't know if you have some additional experience or comments, then you can write me down in the description. Is this completely useless video, or maybe you have some application where you can use this kind of 3D printed timing belts. Anyway, thank you for watching and happy printing.